Okay, today our goal is to study one of the fast Fourier transform algorithms, which is known as the decimation in time. There are many other variants of the fast Fourier transform, but we would not be studying any one of them. So we'll just focus on the decimation in time FFT. And show how the DFT can be solved in a much faster fashion in order n log n operations rather than order n squared operations that you would require if you were to explicitly compute the DFT for the DFT using its exact expression. Okay. So for the decimation in time FFT to really show its magic, what we need is that the sequence which we are interested in computing the DFT has a length which is powers of 2. So assume that xn is of length n equals to 2 to the nu. Okay? So some power of 2. Of course, if that is not the case, then you will just zero pad it. Like if you have a length 100 sequence, you will add just 28 more zeros at the end of the sequence to make it power of 2. Okay? And for sure, you will then have to pay a penalty because you are making your signal being a little longer than it needs to be. And we'll look at a pictorial representation. But in general, FFT really shines when you have a power of 2 signal. Okay. So assume that this is the case, and notice the following. So let's say this is your xn, and I'm going to start from 0. Give some example. 1, 2, 3, 4, 5, 6, 7, 8, and so on. So I have the sequence which is 0, 2, 4, 6. Right? So it takes some values at these indices, and then it has odd indices 1, 3, 5, 7, and so forth. And it takes some other values at these odd indices. Of course, it can be negative valued. I'm just, for ease of expressing this, I'm just focusing on showing positive value signal. Now, if this was my xn, then it's easy to see that I can write this xn as sum of two sequences. A sum of all sequence which is all the odd values, and a sum which is all the even values. So if I do this 5, 7, and I have 0 at the odd locations, 0, 2, 4, 6, and let's call this hn. And collect all of the even values. So 0, 2, 4, and 6. And then put zeros at the odd values. 0, 1, 2, 3, 4, 5, 6, 7. And call this g of n. Then it's clear that this x of n is simply equal to hn plus gn. You just take all its even values, you take all its odd values, you construct two different sequences, and you just add them up. Now, how do you compute this even and odd valued functions? Well, doing that is rather simple. So if I am given xn, I can simply first of all do decimation by 2, okay? And if I do decimation by a factor of 2, then I extract all the even values. So decimation by 2, let's call this h tilde and g tilde n. In fact, in the notation, following notation, let's stay with the notation that I'll use later. I call this as g of en, and I'll call this as h tilde e of n. Okay. So if I want to get all my even values of my sequence, I just do decimation by a factor of 2. If I want to extract all my odd values, then I can first shift my sequence, so left shift by 1, and then I can do decimation by a factor of 2, and I get hn. Okay. So these correspond to the odd value, the odd indices in xn, and of course gn corresponds to even indices in xn. And given these even and odd indices, I can reconstruct my xn by simply doing an expansion by a factor of 2 and doing the appropriate shift of my hn. Right? So it's not hard to convince yourself that if I am given this xn, I'm going to redraw that expression. If I downsample or decimate by a factor of 2 to get gn, and then I expand by a factor of 2 to get gen, then this gen is exactly this thing that I started with. Similarly, if I take this xn, I left shift by 1, left shift by 1, and then I decimate by a factor of 2 to get hn, and then I expand by a factor of 2, then I'll going to get back a sequence which has all the odd values, and it has an odd value 0, odd value sequence index 0. And if I take this and now I take that sequence and so let's call that hen, hen. And if I now right shift by 1 that sequence, then the output of this sequence will exactly be h tilde en. So this h tilde en is what we started with, the odd valued, and if I want to reconstruct my xn, then I just add the two together, and if I add them together, then I get my xn. So what we are going to remember is the fact that indeed I can take any sequence and I can write it as sum of two sequences where each sequence is given by even the values corresponding to the even indices and the values corresponding to the odd indices. Okay? So let's look at what is the effect of this in the frequency domain. So we'll call the Fourier transform of Gen as Ge of e to the j omega. We'll call Fourier transform of Hen as h of e to the j omega. Okay. So Gen is just an expansion of this Gn sequence. If my xn is of length n, then Gn is of length. So I'm decimating by 2. If my xn is of length n, my Gn is of length n by 2. Similarly, I am left shifting my sequence by 1. That still keeps my sequence of length n. And I'm decimating it by a factor of 2. So Hn is of length n by 2 also. Now this gen is expansion of gn. So when we expand a sequence, what happens to the frequencies? The frequencies get compressed. Right? So what is the relationship of ge e to the j omega to the Fourier transform of gn? That is just ge to the j2 omega, right? A compression by a factor of 2. Similarly, he e to the j omega, since we are expanding by a factor of 2, we are getting a compression of the frequencies by a factor of 2. So we get h of e to the j 2 omega. Okay, where this h and g are Fourier transforms of length n by 2 sequences. Okay, so this is what we are going to now use. We also have that xn is simply equal to ge of n plus h tilde e of n, which is simply equal to ge of n plus h e of n minus 1. Okay. So h tilde e of n is simply right shift by a factor of 1, by 1 magnitude. So we can write, so if I compute its Fourier transform now, x of e to the j omega, that is simply going to be the sum of the Fourier transform of these two sequences. So it's going to be ge of e to the j omega plus what's going to be the Fourier transform of h e n minus 1? It will just induce a phase shift. Right? So it's e to the minus j omega times h e of e to the j omega. And now I'm going to plug in the values of ge and he from here. So ge is this and he is this. So I get g of e to the j2 omega plus e to the minus j omega h of e to the j2 omega, which means the Fourier transform of the length n sequence is given by the Fourier in terms of Fourier transform of a length n by 2 sequence and a Fourier which corresponds to, so this g corresponds to the even values of my sequence, right? And this h is the odd values of my sequence. And this is the relationship. Now we are interested in computing the Dft of x. So what is the relationship between Dft and Dtft? It's just samples of the Dtft. So I am interested in computing now samples at 2 pi k over n. Okay. So I get my Dft xk, which is simply equal to x of e to the j 2 pi k over n. Well, I'll just plug in that. So that is equal to g of e to the j 2 pi k over n times 2 plus e to the minus j 2 pi k over n times h of e to the j 2 pi k over n times 2. Okay. Now I'm going to write this as g of e to the j 2 pi k over n by 2. So I just brought 2 down plus wn k h of e to the j 2 pi k over n by 2. Okay, so the Fourier transform coefficient, the Dft coefficients of x are now samples of the DTFT of the sequence G, which is length n by 2, and this factor W and K times the DTFT, sample of DTFT of this n by 2 sequence H. Now let's look at this. What is this? This is just saying that you sample the Fourier transform of G of n at omega equals to 2 pi k over n by 2. So you are sampling the Fourier transform of this G at 2 pi k over n by 2. Similarly, this is simply saying you are sampling the DTFT of H at omega equals to 2 pi k over n by 2. But if you sample this 2 pi k over n by 2, and this sequence, this G is of length n by 2, right? So if I were to, for example, say, let's call this n by 2 as, define n by 2 as equal to n prime. And I say that you are sampling the DTFT at 2 pi k over n prime. What would you say about those samples? You would say that those samples are nothing but n prime DFT of Gn. So effectively, this G of this thing is nothing but your n by 2 point DFT of G of n, right? Because of the relationship between the DFT and the DTFT. So this G of e to the j 2 pi k over n by 2 is nothing but n by 2 point DFT of G of n, where G of n is all the even values of my original sequence. Similarly, we can say that this h e to the j 2 pi k over n by 2 is nothing but n by 2 point DFT of hn. Okay. So moving forward, then, if I define the n by 2 point DFT of Gn as G of k, and I define n by 2 point DFT of h of n as h of k, then what I am saying is that my x of k, the DFT of my original sequence, is equal to the DFT of the sequence obtained by retaining all the even the values associated with the even indices, plus w and k h of k. Okay. So this, I have represented the n point DFT of a length n sequence as sum of two n by 2 point DFTs. Okay. Remember that k in our case is ranging from k equal to 0, 1 up to n minus 1. Now an n by 2 point DFT, by the way, is only going to go up to n by 2 minus 1, but DFT sequence, if you think of it in its relation to discrete Fourier series, DFT sequence is actually periodic, right? So if G of, for example, k is periodic, like G of n by 2, for example, is equal to G of 0, right? DFTs are periodic. If I go above the length of the DFT, I just start repeating the same values. Okay, in general, if you are given an n-point DFT, then its output is periodic with period n. Similarly, for this n by 2 point DFT, g of k is actually periodic with period n by 2. Okay. So this is a well-defined expression, even though gk and hk are n by 2 point DFTs. So up to x, like x0 will be g0 plus wn0 h0, whereas x of n by 2 will be equal to g0 effectively, because g of n by 2 is g0, plus wn n by 2 h0. Okay. Okay, so this is what we need to keep in mind. We can always take a bigger sequence and compute its DFT as sum of two DFTs, where the length of each DFT is just half of what we originally started with. If xn was length 128, then you can compute the 128 point DFT of xn as sum of two 64 point DFTs. So here is an example of what we just talked about, where xn is of length 8. N equals to 8. And what the expression we saw was, if we want to compute x of k, we can compute x of k as sum of g of k plus wn k h of k, where this g of k is the n by 2 point DFT of the even indices, and this h of k is the n by 2 point DFT of the odd indices. So this is what it looks like. You take your sequence, you divide it into even indices and odd indices. You put all of the even indices into an n by 2 point DFT block, and it calculates G0, G1, G2, G3. Similarly, you get, so these even indices are now defining your Gn. Gn's are half the length of the original sequence. So Gn is now length 4. This now corresponds to the odd indices, and the odd indices are defining Hn. They are again half the length. So this is a length 4 sequence. This is a length 4 sequence. Now you take the n by 2 points, so n by 2 in here is equal to 4, and n by 2 here is equal to 4. And every final expression is just sum of these two with one multiplication of w and k. So x0 is g0, so this is what the picture looks like, plus h0 multiplied with w and 0. So you multiply w and 0, this is the line for h0. Okay? And you keep on doing that for x1, x2, x3. Now when you go to x4, you have gone above n by 2. So you now start doing the periodicity by the fact that g of 5 is actually, or g of 4 is actually g of 0. So g of k is simply periodic with period of n by 2, which means that g of 4 will be actually g of 0. So for x4, you get actually g of 0 plus wn4 h of 0. So you bring g of 0, which is given here, down, and you multiply h of 0 with wn4 to get x of 4. and so forth till you get to x of 7, which is actually, instead of G7, because of periodicity, it is G3 plus Wn7 H of 3. Okay? So this is just an example of what we just did, that if you want to compute any n-length DFT, you can compute that by adding two n/2 length DFTs of even indices and odd indices. So the question we want to ask is why would we want to go through this process of dividing our n-point DFT into sum of two n/2 point DFTs? Okay, and for that we'll do some cost analysis of the new DFT computation. Okay, previously, I'm going to ignore specific values, but previously if you just focus on the complex multiplications and complex additions, if you directly use the formula, we had done that in the last lecture, if you computing n-point DFT directly, from the formula, it involved about n squared multiplications and complex valued, and about n squared additions. Again, we are only focusing on complex valued, which means total of approximately 2n squared operations. Okay. So whenever we compute n-point DFTs, it's going to cost us about 2n squared operations, right? Roughly. Now, let's look at what happens if we compute h, k, and gk and then add them up. So what is happening there? To compute g of k, so g of k is an n/2 point DFT. If we just look at above, we need about 2 times n/2 square operations. To compute h of k, again we need approximately same number of operations. So the total number of operations that we need to carry out is so total cost of two n/2 point DFTs, that is simply equal to 4 times n/2 square, which is equal to n squared. Now, at the end of the day, so we get these two sequences. Again, writing down x of k equal to g of k plus h of k times wn of k. Okay, so the cost of this plus this is n squared. But to compute x of k, what do we need? We also need to do one addition and one multiplication. Okay, so to do the final computation, we also need n additions, complex additions, and n complex multiplications. So we also need n additions, everything is complex here, and n multiplications. So what is the total cost if we were to compute the DFT using this division into two sequences? Well, that is then total cost of computing xk, that is equal to, we have this n squared, we have n multiplications, we have n divisions, so that is n squared plus 2n. Okay. So let's compare then. Previously we had 2n squared. Now we have n squared plus 2n. Now, for any reasonable value of n, as long as n, so I can write this 2n squared, of course, as n squared plus n squared. Right? So when will this division be beneficial to me? Whenever whenever 2n is less than n squared, we have a lower cost. Which is of course true for any reasonable value of n. 2n will be always smaller than n squared. Of course, we haven't saved that much. We are 2n squared versus n squared plus 2n. But the natural question to ask is, now remember, we started with x of n, okay, and we divided it into gn and hn. So if the length of xn was n, we ended with two sequences which had length n by 2 and n by 2. And we said, now compute the DFT of gn and hn. But we could ask, well, there's nothing different. We are asking to compute n by 2 point DFTs. Why don't we do the same trick that we did earlier? Think of gn as another sequence. So previously, for example, xn was 8, gn was length 4. Well, think of gn as a length 4 sequence. We can compute its DFT using the sum of DFTs of two length n by 4 sequences. So I could say that, well, let's divide this gn into two sequences of length n by 4 and n by 4 and compute their DFTs. And similarly divide this hn into length sequences of n by 4 and n by 4. And we can keep on doing that. We can keep on doing that till we end up with only length 2 sequences. Right? So we don't have to stop at n by 2 or n by 4 and n by 8. We keep on doing it till we end up with just length 2 sequences. And in each stage, we are saving some cost by going to a smaller length sequence. And the hope is that at the end of the day, we end up with a cost which is much smaller than n squared. So how many stages we can do? Remember now our goal that we have power of 2. So length is n equal to power of 2. So we said n is 2 nu. Right? So at stage 0, you had a length n sequence. Okay, whatever number I put here, that will be the length of the sequence. What happens at stage 1? We get two sequences. So this gets divided into n by 2 and n by 2. At stage 2, this n by 2 further gets divided into n by 2 and n by 2, which means we end up with 2 more sequences due to this sequence of length n by 4, or I can write as n 2 to the 2, right? And n 2 to the 2. And similarly for this, n 2 by 2 and n 2 by 2. In stage 3, each one of these n 2 to the 2 sequences get divided further into 2 sequences. So this will be divided into n 2 to the 3 and 2 to the 3. This one will get divided into n 2 to the 3, n by 2 to the 3, and n by 2 to the 3. Similarly, this one, n by 2 to the 3, n by 2 to the 3. And similarly, this one will be divided into 2 also, n by 2 to the 3, n by 2 to the 3. And we can keep on doing that till we get at stage of log of n base 2 minus 1. Okay. So which is equal to nu minus 1. So I'm saying n equal to 2 to the nu. So log n to the base 2 will be nu minus 1. So if you just follow this trend, at every stage I end up with sequences of, all the sequences in a stage are of length what? They are n divided by 2 to the stage level. So here the length of sequences is n divided by 2 times the stage, right? So n by 2 here, n by 2 square here, n by 2 cubed in stage 3. So at this stage I will have sequences of length n divided by 2 to the nu minus 1, which is equal to 2. 2 to the nu divided by 2 to the nu minus 1. I'll get sequences of length 2. And how many sequences do I get in each stage? If you look here, the sequences that I get are 2, the sequences that I get are 4, the sequences that I get at stage 3 are 8. So at every stage I get the number of sequences equal to the number of the stage. So I get at the stage log n to the base 2 minus 1, I get length 2 sequences and I get total of nu minus 1, 2 to the nu minus 1 sequences. Okay. So at every stage I have 2 to the stage level number of sequences. So at this I get total of 2 to the nu minus 1 sequences. Okay. And of course the total number of samples or total number of values stays the same at each stage, right? It is, if I multiply 2 times 2 to the nu minus 1, I get 2 to the nu, or n, total of n values. Okay. So what this is saying is we keep on dividing. We actually don't compute the DFT at any stage. We actually keep on dividing our sequences into factors of 2. Every time a sequence is simply given by the sum of the sequences, which are sum of 2 smaller sequences DFTs, right? So we had originally x of k equal to g of k plus w n k h of k. To compute g of k, we'll actually not compute it directly, but rather we'll say g of k is equal to G2 of k, where G2 of k simply means the even valued sequence associated with G of k, plus W of n by 2 k H2 of k. Okay, and similarly G2 of k is simply given by its next stage, which is G3 of k plus W of n by 4k H3 of k. And we keep on doing that till we are left with a sequence which has length 2. So let's think of a length 2 sequence. What does the DFT, how do you compute the DFT of a length 2 sequence? So suppose we have a length 2 sequence. S of n. Okay. So the 2-point DFT of that S of k using the formula is given by what? If you want to compute the 2-point DFT, you just take the DFT of its even value, which is length 1, multiply it with W 2 to the k and times the length 1 sequence, which is given by the odd value. So S of k, this is a capital S, okay? That is simply equal to S of 0 plus W2k S of 1. Okay? Which means that S of 0 equals little s0 plus S1, because W20 is 1, and S1 is equal to S0. Now W21 is minus 1, so minus S of 1. Okay? So it means that if you want to compute the 2-point DFT of a sequence, that is simply given by this butterfly diagram. So you are given, this is the time domain S0, S1, and the DFT S0, S1. That is simply given by you multiply. S0 is given by simply sum of S0 and S1. And S1 is simply given by S0 and S1, but S1 gets multiplied with minus 1. Okay. So computing the 2-point DFT simply involves 2 additions. And if you want to count minus 1 as a multiplication, you can count that. Otherwise, it's just 2 additions and no multiplication. So that's the idea behind decimation in time DFT. You actually never compute the DFT explicitly. You keep on dividing it into smaller and smaller subsequences. And then you simply use this expression. The only thing you have to worry about is multiplication of Wn by 2k, which depends upon the stage. Okay. So let's take a look at an example of this for the same length 8 sequence that we did to clarify this further. So we are back at that n equal to 8 example, and we had originally said, well, take that sequence and divide it into even and odd parts and then compute the 4-point DFTs. But in reality, what we can do is, for each of those 4-point DFTs, we can further divide them into even and odd sequences. So the even sequence of the sequence we had previously is x0 and x4. And the odd sequence of that was x2 and x6. So we divide that into, so right now we are computing g of k equal to g2 of k plus wn by 2k h of k, okay, h2 of k, where g2 of k corresponds to the even indices of g of n, and h2n corresponds to the odd indices of g of n. Okay. So we divide it into two pieces, and now we compute the 2-point DFT. So this is a 2-point DFT of each one of these to compute G0, G1, G2, G3, and similarly we can do for H0. If we do that, then we end up with this diagram. Okay. We said initially you can start with, so you had x0, x4, you compute their n by 4-point DFTs. Then you get x2, x6, you compute their n by 4-point DFTs. And you multiply them with wn by 2k, okay, and wn by 2, 1, 2, 3. Now remember that wn by 2k can also be expressed as wn2k. Right? So this is what the book is doing. It is, instead of saying wn by 2, 0, wn by 2, 1, wn by 2, 3, it is writing wn 0, wn 2, wn 4 because of this relation. Wn by 2, which is simply e to the minus j 2 pi k over n by 2 is simply equal to e to the minus j 2 pi times 2k over n. So this whole block, the output of this is effectively G0, the output of this is G1, the output of this is G2 and G3. Okay? And similarly, the output of this is H0, H1, H2, and H3. Okay? And after this part, after this stage, the next stage is what we had seen earlier, that if you want to compute x0, that is G0 plus H0 times Wn0. Okay, so now we are left with this 2-point DFT. But we just saw that each of the 2-point DFTs can be further divided as just a simple butterfly diagram. Right? The 2-point DFT is simply given by this butterfly diagram. Okay. So this 2-point DFT can be simply given by connecting this to this and this to here and like this and multiplying this with minus 1. And if you put all of this together, you get your complete butterfly diagram, which is simply given by, you start with x0, x4, these are the 2-point DFTs. Okay. Similarly, here are the 2-point DFTs. After this, you now take these output and apply the next level to compute the 4-point DFTs here. Okay. These are 4-point DFTs. And again, you apply recursively the same expression to compute the 8-point DFT, which is this whole thing. Okay. So DFT, computing the DFT can be simply done using this recursive expression, you start with a sequence, keep on dividing it up to 2. The only real thing you compute is this 2-point DFT. Then you go back, you do some more multiplications, compute the 4-point, 8-point, 16-point, 32-point, and you keep on going, whatever was the length of the sequence. If you had a bigger sequence, if you had, for example, a 16-point DFT, you would have done the same thing again after this. You would have one block which looks like this, another block which replicates this. You multiply them in the right way to get a 16-point DFT. Okay. So we'll do the computation of what is the eventual cost of this operation, because we never actually end up computing the DFT explicitly. At every stage, we are only doing simple multiplications with Wn to some power and additions. That's it. You can try to remember this butterfly diagram by thinking of, like, now you can start counting your stages. For example, previously we were starting from the end point and going backward. Right? We had a length 8 sequence, we went to length 4, 2 sequences, then we went to length 2 sequences, a total of 4. If you want to go from this end to the end point, then actually every computation is simply given by this butterfly diagram. So if you look at this, you have this butterfly diagram and the gap between the values that you take in is always n by 2. Okay, so at this stage, for example, you had x0, the next value is x4. Okay, you have x2, the next value is x2 plus n by 2, which is x6. Okay, so the gap between them is always n by 2, which in this case our n was 8, so our n by 2 is 4. Okay, so here we have again a gap of 4, and then we go to x1, again we have a gap of 4, till we run out of all the values. Okay, and if you, for example, focus on this stage, and if you treat, for example, this as a value, if you treat this point, if you treat this point as a value and this point as a value, right, then again you just have a butterfly diagram connecting the two. You have this connecting to, so you have a connection from here to this value, and you have a connection from here to this, and you have this connection. Okay, so within each stage you see this kind of a butterfly diagram again and again. And similarly, if you come here, you think of this as one value. Let me change the color. Think of this as a value and this as a value. Again, you have a butterfly diagram which is like this. With, of course, the right multiplication factor. Okay, so these butterfly diagrams just keep on expanding as you go away and away from your sequence. Okay. What we want to now do is look at the cost of doing this recursive division to find out what is the final cost of computations in DFT, as opposed to using the direct formula. Okay, so I just want to remind you at the first stage, so stage 1, where we took our n length sequence and divided into two n by 2 sequences, and we said now compute the DFT of each n by 2. we ended up with this cost, n plus 2 times n by 2 square. Now at stage 2, we'll take that n by 2 sequence and we'll apply the same formula to that one. So we have this n, and now our new n is n by 2. So we get n by 2 plus 2 times n by 4 square. So if we now stop at the next level where we said now we have length n by 4 sequences and we want to compute their direct DFT, then the total cost will be this factor. I am just plugging in this formula here where n is replaced by n by 2. So the total value that will come up is n plus 4 times n by 4 square. Okay, so effectively this is how many sort of times you have done the division. So this is stage 2, and this is effectively the residual cost of DFT that you want to compute explicitly. So this is like the residual cost. Okay. Now if you just say at stage M what is my cost, then what ends up being is you get n plus how many of these n's you get? You get m of these plus the remaining cost that you are left with is 2 to the m times n divided by 2 to the m square. Okay, these are the number of sequences that you are left with. And these are the length of the sequences. So this is the residual cost. You want to now compute the 2 to the m point DFTs, n divided by 2 to the m point DFTs, and each one of those is going to cost n divided by 2m square, and 2m is the total number of sequences. So let's go to the final stage, the stage where we have stage log of n to the base 2 minus 1. Okay. So you are left with n plus, so you have a total of log n minus 1 plus the cost of the next stage, which is simply, now if you think of what is the cost of computing the 2-point DFT, that is simply, if you remember the butterfly diagram, if you want to compute the 2-point DFT, all you had to do was do one addition here and one addition here, discounting the cost of multiplying with minus 1. Right? So how many sequences you have? At the very last stage, how many length 2 sequences you have? 2 to the new minus 1 sequences. Okay? And the cost of computing, so this is the number of sequences you have, and the cost of computing the 2-point DFT of each sequence is simply 2. So which is equal to 2 to the new, which is n. So this means that you get your total cost is, you had first log n to the base 2 minus 1 plus another n, so you have log n to the base 2 number of n's. That is equal to simply n log n to the base 2. Okay. So by doing this recursive partition of your power of 2 sequence into smaller and smaller sequences, you end up actually never computing explicit DFT till you reach the length 2 sequence, for which computing the DFT is trivial. And if you add up all the costs, then you come up with a cost which is order n log n to the base 2. Okay, we have ignored constants, small constants here, which is I think like the relevant constant is perhaps 6. But the point is that this is much, much smaller than the original n squared cost that you would have incurred if you had used the formula as it is. Okay, so that's what the power of using this decimation in time FFT is. You actually end up doing the computations in a much cheaper fashion than doing explicit computations. Now, this is a plot which is showing you the cost of doing FFT in MATLAB, and the cost is expressed in terms of the floating point operation, which is a representative of just the total amount of time it will take you. Okay, and these plots are actually showing you two extremes, showing you the cost difference depending upon what kind of a length of sequence you are using. So this plot, this dashed plot, actually corresponds to 6n log n to the base 2. Okay, this plot, you will reach this value if n is a power of 2. If n is a power of 2, you exactly hit this curve. Okay, it's really cheap. But as you keep on increasing or keep on making n away from power of 2, you will have to incur additional cost because of zero padding and all those other factors. Okay, you can't make FFT if you tell FFT to compute an FFT. If you tell MATLAB using some n which is not a power of 2, you will not be living on this set. This curve, on the other hand, is a curve of 6n squared. Okay, which is the worst case, and this corresponds to n which are prime. So if you give MATLAB FFT n being prime, it's going to perform as worse as if it had to explicitly compute the DFT formula. Okay, and in between, if you give MATLAB FFT some other value of n, it will give you plots in between. So just doing FFT is not enough. If you just take MATLAB FFT and say like, I'm using FFT, I should get a good performance, that's not going to work till you really focus on giving it a power of 2 sequence. Okay, you either zero pad it or you make it power of 2. You work with power of 2 sequences. If you don't do that, then as this plot shows, if you work with prime n's, then actually you might as well be just using the explicit formula. You don't even have to use FFT. Okay, so this is just a plot from your book. You can read more about it. That pretty much concludes what I want to talk about FFT. There are many other algorithms for computing FFT. Some use some nifty tricks to reduce the cost even further. There is also other variants. Decimation in time is not the only variant of FFT. But in all of those methods, the basic idea is based upon the fact that you keep on recursively dividing your sequence into smaller and smaller sequences. Okay, so if you get the sense of what decimation in time FFT does, you shouldn't have a hard time understanding others if you are interested in learning those. But for the purpose of this class, we'll stick with decimation in time.